In this video lesson, we are looking at something called the reaction quotient, which has the symbol Q. So to do this lesson, you might want to have a copy of this handout, the reaction quotient. We know that if a reaction is at equilibrium, then the K equilibrium is constant. And what this means that the concentration of our products and the concentration of reactants is going to stay the same. So once it's at equilibrium, the ratio of the concentration of the products and to the concentration of reactants stays the same. However, before our reaction actually meets equilibrium, the ratio is not constant. So that makes sense because we know that the reaction is moving towards equilibrium. So the concentration of products and reactants is going to change. So if we know the concentration of reactants and products at any time during the reaction, we can calculate or we can determine a couple things. The first thing we can figure out is whether or not the reaction is actually at equilibrium. The second thing we can figure out is if the system is not at equilibrium, which direction it needs to shift in order to reach equilibrium. So really, it's one or the other of these things. So you're either figuring out if you're at equilibrium or which direction you need to go in order to reach equilibrium. In order to determine these things, we do something called calculating the reaction quotient, so our Q. And we do this in a very similar way that we established yesterday when we talked about calculating K equilibrium. So we're going to calculate Q a very similar way that we calculate K equilibrium. And I'm going to show you the formula using the same pretend reaction. So little a, capital A plus B, capital B, reacts to produce C, capital C, and D, capital D. So remember that the small letters are our reaction coefficients, and the big letters represent our actual compounds. So our formula for reaction quotient is this, exactly the same as the K equilibrium formula. Okay, so our concentration of our products are over our concentration of our reactants, and they are to the exponent of their coefficients, like we see here. The thing to note here is that we're using exactly the same formula as K equilibrium, but we're using different concentrations. And the concentrations we're using to calculate reaction quotient are not necessarily those concentrations at equilibrium. The reason we look at calculating reaction quotient is because it can tell us which way the reaction must shift in order to reach that equilibrium. Basically, what we do is we're going to compare our reaction quotient to our K equilibrium. If our Q is less than K equilibrium, then the reaction needs to shift towards the products to reach the equilibrium. If our Q equals K equilibrium, then our system is at equilibrium. And finally, if our Q is greater than our K equilibrium, then the reaction needs to shift towards the reactants to achieve the equilibrium. And I just added that it's shifting left to do that. And this is because the product to reactant ratio is too high. So we're going to do an example of comparing a Q to K equilibrium. So when you have this done, flip your page over. So here's our example. We have that reaction of nitrogen gas plus hydrogen gas making nitrogen trihydride, NH3. So we want to know the reaction. The reaction needs to shift in order to reach equilibrium at 450 degrees Celsius if the K equilibrium is 0.064. And at this point, the reaction has these concentrations. So you don't have these on your page, so you need to copy these out because Right now, the reaction has 4.00 mole per liter nitrogen gas, 2.0 times 10 to the negative 2 mole per liter hydrogen gas, and 2.2 times 10 to the negative 4 mole per liter of NH3. So in order to figure out the direction a reaction needs to shift, we need to calculate Q. So based on our general formula for Q, if we sub in our reactants and our products for this reaction, our equation for Q is going to look like this. Concentration of NH3 squared divided by concentration of nitrogen times concentration of hydrogen cubed. So if we sub in our concentration values, we get something that looks like this. 2.2 times 10 to the negative 4 mole per liter squared divided by 4.0 mole per liter times 2.0 times 10 to the negative 2 mole per liter cubed. And then if we do the math, we get Q equals 1.5 times 10 to the negative 3. So remember, we ultimately want to compare our Q value to our K value. So our Q is 1.5 times 10 to the negative 3, which really equals, if we expand that out, 0.0015. So from our question and our given information, our K is 0.064 and our Q is 0.0015. So that means that, therefore, our Q is less than K. So therefore, the reaction is not at equilibrium and it's going to shift right towards the products. So that is the end of this video lesson. Remember, the ultimate reason behind calculating the reaction quotient is so you can figure out which way a reaction needs to shift in order to reach that equilibrium. So I'll have some practice posted for you later, and that's all for now.